On this week's GARNet Research Roundup, I'm really delighted to be joined by Dr. Ranjan Swarup from the University of Nottingham. And we're going to be talking about a paper just come out in Nature Communications. That is part of actually 3 papers that have come out from the same research groups. And the title of the paper we're discussing today is A Mechanistic Framework for Auxin-Dependent Arabidopsis Root Hair Elongation to Low External Phosphate. So I'm really happy to chat to Ranjan today. So we used to be colleagues. So when I did my PhD, I worked with Ranjan on kind of the very early work in this area. So it'll be great to hear a summary of this work and where you've got to with this, Ranjan.
Okay, Kiran. So very nice to speak to you. So yes, as you said, this paper is about mechanistic framework about how low phosphate can trigger root hair elongation. And this particular paper that we have done, this is an Arabidopsis, and as you mentioned, that we have got another paper in Nature Communication, which is part of the back-to-back manuscripts that we submitted, which is on rice. And what we have shown in this paper that how low phosphate can impact root hair elongation. It is known for a long time that low phosphate can trigger root hair elongation, but now we have provided a mechanistic framework that how it happens, and what we have shown that under low phosphate there is increase in auxin biosynthesis, and what we have shown that there is a key enzyme in auxin biosynthesis, TA1, that is upregulated in response to low phosphate, and that result in increased auxin synthesis in the root apex. And once that auxin is synthesized, then that auxin needs to be moved to the root hair zone, and that is facilitated by one of the key auxin influx transporters, Auxin. And what we have also then shown that Auxin mutants as well as TA1 mutants, they have defect in root hair elongation, that in response to low P, they do not really show root hair elongation phenotype. So what in this paper we have very clearly shown that under low phosphate you need auxin, there is a fresh auxin synthesis that result in more auxin produced in the root apex. That auxin is then moved by Auxin into the root hair zone, and once it's there, it can then induce key transcription factor, RF19, that result then in somehow root hair elongation. And what we have also tried to then do is to identify some of the key downstream targets which RF19 can affect. And 2 of the key targets that we have defined in this paper, which is RSL2 and RSL4. RSL2 and RSL4 are 2 key genes involved, which have been implicated in root hair elongation. And what we have shown that RF19 can directly upregulate RSL4. And in a related manuscript, though this work is not part of this manuscript, but what our results indicate that RSL4 promoter can be directly regulated by RF19. So we have identified the auxin response elements in RSL4 as well as in RSL2. Okay. So we are quite pleased the way this work has gone, and it provides really that we know that low phosphate can regulate root hair elongation, but now we have provided certain insight how this works, and it can be extremely useful for future crop improvement program. And now we know what are the genes and signals that can regulate root architecture or root hair.
Okay, great. Thanks very much, Ranjan, for that summary. So, I mean, the beauty of the paper is that it's really stepwise work that you find this relationship between phosphate and auxin, and then you look that it's synthesis of auxin, the transport of auxin, and then the downstream regulation is all key within this process. So it's a real stepwise through. So the AUX1 protein is expressed in many areas within the root tip. So what sort of experiments did you do to find out where precisely the localization of the AUX1 is important for this phosphate response?
So what we did, we know that AUX1 is expressed in several different domains in the root apex. So what we did, we used certain molecular tricks to only use some of the expression domains of Auxin using a process called transactivation.
Okay.
And using this, we expressed Auxin only in lateral root cap cells and epidermal cells. So lateral root cap cells provide the conduit for movement of Auxin from the root apex into the root hair zone and in the elongation zone. So when we use these lines in which Auxin was expressed only in the lateral root cap cells and in the root hair zone in the epidermal cells, I should say not root hair zones, Auxin was expressed in the epidermal cells. And we could show that by expressing Auxin in those cells, we could rescue the root hair defect of Auxin mutants. So that very clearly suggests that those are the expression domains of Auxin, which are crucial for this root hair elongation response under low P.
Okay, I see. And you mentioned earlier about the Auxin biosynthesis gene, so TAA1 is upregulated. But you also show within the paper that a gene which is involved in Auxin or IA degradation is also upregulated. So that relationship doesn't seem quite as straightforward. So do you have any insights about how the Auxin degradation mechanism is involved in this process?
So at the moment, we don't really understand this fully, but what we believe that maybe this could be part of Auxin, some sort of attenuation response after the Auxin levels have been upregulated. Maybe they need to come down to normal levels. And what we have shown, in fact, in this paper, that we have got two alleles of DAO1. DAO1 is an Auxin degradation enzyme. Mm-hmm. We have got two alleles, one which is the null allele, and the other which is a dominant gain of function allele. And in the dominant gain of function allele, we find the root hair defect. In this dominant gain of function allele, we find that there is lower levels of IA, presumably because more IA is being degraded. Mm-hmm. And in this one, we see the phenotype, but not in the null allele, we see the phenotype. Okay. So it is consistent with our data that basically under low phosphate, there is increase in Auxin biosynthesis resulting in increased Auxin accumulation in the root hair zone that result in root hair elongation.
Yeah, I see. Okay. And finally, you mentioned the rice paper earlier. So this is a really lovely example of using, obviously, the model, which has got a lot of genetic tools available, Arabidopsis, but then translating this work into extremely relevant crop. So can you quickly touch upon the results that you show in the rice paper to basically follow up from what you see with the Arabidopsis paper?
Yes, I think it's very interesting. In fact, in this case, we first saw some of the effects in rice, and then we moved into Arabidopsis because of the pulses and tools that we had at our disposal. And it all started initially when we were, in fact, looking at Auxin mutants in rice. And we did some CT scans and all, and Auxin mutants, which have big gravitropic roots, and CT scans clearly showed that Auxin mutant had a very shallow roots. And we then suspected that Auxin mutants should have improved phosphate uptake because phosphate P is one of the shallow soil resource. So when we started looking for improved phosphate uptake or P uptake in these Auxin mutants in rice, we realized that is not the case. And that is how, in fact, we started to look into this in more detail, and then we realized that these Auxin mutants are not showing this low P-mediated root hair elongation response, and that basically provided us this insight that Auxin is critical for this low P-mediated root hair elongation. So once we saw that in rice, then we tested this in Arabidopsis, and we find that it is a similar sort of a response in Arabidopsis as well, and we also use some cell biology tricks and other tricks to basically show that there is increased Auxin accumulation both in rice as well in Arabidopsis in response to low P. So that's the insight in this case we gained from our rice, and then tried to provide more mechanistic framework in Arabidopsis.
Okay, cool. And that other rice paper has some lovely images using the CT scanner that you have there in the Hounsfield facility in Nottingham. So, okay, so that's really great. Thank you very much, Ranjan, for discussing the paper. And as we discussed before we started chatting, that it's been well over a couple of years, if not more, in the making these papers. So I'm sure there's plenty more going on in this area, and we look forward to hearing all about it much sooner, hopefully.
Yeah, hopefully. I think we are now, in fact, working on. We are working on improving root architectural traits and how we can, in fact, impact a nutrient uptake, because root architecture is crucial for nutrient and water uptake, and very often it has been not really got this sort of attention, but in recent years, with the efforts of lots of people, including Malcolm Bennett, Jonathan Lynch, and others, in fact, there is more emphasis on on root architectural traits. Mm-hmm. And we start to understand a little bit better, and hopefully, still there are not many genes, in fact, that we know that can impact root architectural traits, and that's where the research is going in from research from our groups and other groups. In fact, we are working on different traits that can alter root architecture, and can we use some of those genes that we know in improving resource use efficiency of our plants.
Absolutely, and it absolutely states that working in Arabidopsis is key for those crops as well, because you need this back and forth between the two organisms. The power of the genetics versus the important phenotypes, which are going to be important for improving productivity.
That's absolutely right. I think with all that tools and resources which are available in Arabidopsis, and very simple genetics and lots of other amenable features of Arabidopsis, makes it extremely efficient model system. But we are also, in fact, rice is also becoming a good model system in its own right as well. Yeah. But yes, we hope that what we learn from Arabidopsis can be translated into other crops.
Excellent. Okay. All right, we'll leave it there, Ranjan. Thank you very much for chatting to us.
Thank you, Karan.